Hello everyone, my name is Antonio Zuniga, and this presentation on Linux Ubuntu 12.10 was created by myself and Robert Ramdhan. It gives a brief overview of concepts we learned in class and how they are implemented by or relate to Linux Ubuntu 12.10. So let's get started and on to slide 2. So a quick intro to Ubuntu. It is a free and open source GNU Linux distribution and operating system. The GNU is the open collection of software that Linux came from, which has been worked on since the 80s, and consequently the first version of Linux came out in 1991. And all Linux distributions were created with a free-to-use philosophy in mind, so anyone could have the opportunity to build upon the source code with their own revisions, make their own kernel, just to make it their own way. It contains features and applications similar to that of the Mac OS or Windows OS, which can handle everyday computing tasks. And it was designed to just make everyday computing tasks simple, especially with the X Windows system and simple layout. It's not hard to use, not like having only a command line and having to use those kind of instructions. They had the average consumer in mind when making this. And it can be summarized as the glue that lets you take a single CD, install hundreds of separate pieces of software, including the GNU software and the Linux kernel, and have them work together as a single integrated desktop system. So Ubuntu is the precompiled package software that goes with the Linux kernel, and that gives the user a nice, comfortable computer environment. That's what Ubuntu is all about, and it's better than just a command line, and the user has access to thousands of graphical applications. So the picture you see here is a complete Linux OS. Contains obviously the kernel, the libraries, the compiler, and Ubuntu would take this and then add hundreds of extra applications to make it convenient for the user. And on to slide 3. And here's some info about the kernel and tasks and architecture. The latest kernel version packaged with the Ubuntu 12.10 release was 3.5.0. The latest kernel in use now is 4.8 with Yakety Yak, the most current version. And this version is named Quetzal, and each distribution comes with a unique name. I may have said that earlier. Coming out semi-annually, so about every 6 months, and each version number is simply the year and the month it came out. So Ubuntu 12.10 came out in 2012, October, and that's why it's 12.10. The kernel is different in that the first number is the core kernel version number, which, if that changes, basically the whole major changes in the source code and the whole architecture changes. And that's only been done 3 times since the first one in 1994 when they started this numbering convention. The second number denotes a major revision of the kernel version, and the third number is a minor revision. If you see a fourth number, it's just they took care of some bug fixes or security patches. The kernel can be regarded as an enhanced machine that, in the view of the application, abstracts the computer on a high level. All applications and processes Ubuntu has to offer do not come in contact with the hardware itself, except the CPU. Only the kernel does. The kernel is the lowest level in the hierarchy as far as the applications are concerned. The CPU is the exception because obviously the programs have to access it, but the full range of instructions are not available for applications. And as you can see in the diagram, the system calls are the interface between the user applications and the kernel itself. So if a user application sends a request for the kernel to get the task accomplished. It's going to prompt a system call, and it can also a request can come from the kernel or lower, maybe even from hardware, and that could prompt a system call that will affect the user application. So it's like the gate. It's how the applications can communicate with the kernel. Either way, it all gets handled by the kernel. The kernel is the brains of the operation. And as you can see on the right, more in-depth view of the kernel itself, some of the tasks it takes care of, process management, memory management, the file system, device drivers. That's where everything is accomplished, whether it's coming from a hardware input or a user application input. And on to slide 4. The kernel can also be viewed as a resource manager when several programs are run concurrently on a system, which is usually the case. And in this case, the kernel is an instance that shares available resources, CPU time, disk space, network connections, between the various system processes, while at the same time ensuring system integrity. So that's a lot to do, and that's why the kernel is so important. And an example being the CPU time. The kernel's got to decide how that time is shared, and important processes are given larger share of the CPU time, less important processes a smaller share. So as you can see on the right side of the picture, the process management, that's going to be that department, and something like the virtual file system is how the kernel organizes all its files that shares its data. And on to slide 5. What levels does Linux support? Linux Ubuntu is an operating system, so level 2, the ISA, and level 3, operating system machine level, are supported by the operating system, which is just very particular software that does a very important job. Obviously the most important software in a computer system. The operating system machine level instructions are interpreted by the OS, which produce ISA level code, binaries for CPU execution. So there's a built-in C compiler, and it's going to compile these OS instructions to binaries. In between that, going to the binaries and the compilation, there's an assembler that converts the assembly language into that machine code, and the linker is going to connect those machine code files to an executable to run on the CPU. And it depends on which ISA as to what the binaries are going to look like and the assembler instructions used to create them. So in this example, you're seeing the 86 architecture. And on to slide 6. Okay, so some information about virtual memory and techniques. The kernel creates a new virtual address space in 2 situations with the Linux environment. When a process runs a new program with the exec system call, and when it's created by the fork system call. The exec system call is easy to do, and the process is given a completely new and empty virtual address space. The fork instruction has to create a copy of the existing process, and the copy needs an identical address space to the original. The kernel copies the parent's process descriptors, then creates a new set of page tables for the child. The parent's page tables are copied directly into the child's, so now the 2 processes occupy the same physical memory, but of course different virtual memory, because the virtual memory is what the programs see, and the physical memory, as we remember, is the actual hardwired memory. And on to slide 7. Okay, so some more on virtual memory and techniques, particularly swapping and paging. Early Unix systems swapped out the contents of entire processes at once, and Linux does not implement whole process swapping at all and uses the paging technique exclusively. And a refresher on paging: it's the movement of individual pages of virtual memory between physical memory and disk. And in Linux, they have what's called a swap space, which is the same thing as paging. It's not the same as a whole process swapping, as explained earlier, and it is just basically computer memory management involving swapping regions of memory to and from storage. So that's what Linux calls its paging, and the swap space is that partition of a hard disk that it uses to actually do the paging. And in the system monitor, the picture on the bottom right actually has a percentage of how often that happens and how much memory has actually been swapped. So it's a pretty interesting feature. And that is it for this slide. So on to slide 8. Okay, page replacement algorithms. The Linux kernel takes advantage of two algorithms: the least recently used and the FIFO algorithm in the second chance version for its page replacement algorithms. The LRU actually uses a doubly linked list to organize all the pages in the system, which I thought was pretty interesting. And the way it works is the list is resorted each time memory is accessed, and the page in question is found and moved to the start of the list. Eventually, you will have an equilibrium in which frequently used pages are at the beginning of the list and least used pages are at the end of the list. So it's an efficient replacement algorithm. Alright, and next page, or next slide. Okay, so now a little bit about the MMU. Memory management refers to the operations implemented by the operating system to provide memory to applications. In Linux, Ubuntu, memory management is built on this unit that we call the MMU. And the MMU's function in Linux Ubuntu is to translate physical memory addresses to linear addresses used by the operating system and request a page fault when the CPU tries to access the memory that is restricted to it. And next slide. Okay, fragmentation. ext4, which is the file system used by Ubuntu, allocates the files differently than Windows PCs. Ubuntu will scatter the different files around the disk, which will leave large amounts of free space between them. If the file size increases, there will be free space to allocate that data. If fragmentation does happen in Ubuntu, the file system will allocate the files around the disk to reduce disk fragmentation without the need of the defragmentation tool. Ubuntu is designed to avoid defragmentation. However, there will be signs of fragmentation if, for example, the file system is 95% full. So it's interesting how they designed it so there would never be a need for user defragmentation. Very convenient and just efficient for the memory itself. And on to the next slide. Alright, a little bit about segmentation. In Ubuntu Linux, segmentation use is actually very limited. Ubuntu prefers paging as opposed to segmentation. One of the design plans for Ubuntu is a wide range of architectures for portability. The RISC architectures have limited support for segmentation. And a segmentation fault in Ubuntu is when part of the memory cannot be accessed or does not exist. The process of segmentation divides all available memory into segments. If Ubuntu encounters an error when writing to a memory segment, the operating system will send a SIG-SEV signal to the program, which will crash it and display the segmentation fault message. So this picture on the bottom is pretty cool, displaying how the segmentation algorithm works pictorially as opposed to the paging, which is what Ubuntu Linux, of course, prefers much more than segmentation. And that is it for that. On to slide 12. Alright, hardware virtualization. In Ubuntu, the default virtualization technology is KVM, kernel-based virtual machine. And to check to see if hardware virtualization is supported by the CPU, you can use the following commands. The top one for the Intel processor, and the bottom one, the SVM, used for the AMD processor. So it depends which architecture you have. One may not be able to comply with being or creating virtual machines, and one may be able to do that. So you'd use these commands to see if you could. Alright, and that is it. Thank you for listening, and I hope you enjoyed it.